And the next talk is online and will be given by Connor Ryden. And we'll hear about revealing systematics in strong lens substructure with CNNs.
Thanks. I assume everyone can see and hear everything. Yeah, I'm Connor Ryden, and I'm a postdoc in Simona Vigetti's group here at MPA. And I'm going to talk today a bit about how CNNs have helped us to understand some of the systematics in our work, which is detecting dark matter substructures in strong gravitational lenses. So I just remind everybody a little bit about how this works. We work on strong lensing, where a foreground galaxy is lensing the light from a distant background galaxy. And if there are dark matter substructures in the vicinity of the lensing galaxy or somewhere along the line of sight, then these will have an effect on the gravitational lensing. So with very precise modeling, you can actually infer the presence of these dark matter substructures. A really important part of doing this is sensitivity mapping. And that's basically where we'd like to understand how sensitive is our strong lens observation to a given mass of substructure. And this gives us a bit more statistical power because most of the time we're not detecting any substructures. They're too small to be seen in the data. A detection is a rare thing. And so we want to be able to get some constraints from non-detections. Now, doing this type of statistical, this sensitivity mapping is very expensive. And so that's where the machine learning comes in. And for the past 2 years now, I've been working on replacing the sensitivity function with something machine learning based. So the idea is fairly simple. There's a large ResNet that looks at images of strong lenses, and it classifies them as either having substructure in or not. And then to produce the sensitivity for a single observation from there is quite straightforward. We basically make many realizations of the same strong lens system, moving the dark matter substructure across all the positions in the image and over a range of masses, substructure masses that we're interested in. And then with all these realizations, you pass them through the detector and record the detection significance. And that gives you something like what you see in the middle here. Basically shows for different masses in different positions on the lensed images, how significantly could we detect an object of that mass. And so if you choose a detection threshold, significance threshold that you're happy with, then you can read off the mass you would detect with that significance everywhere in the image. So previously we've used that to make some forecasts for Euclid and the sensitivity of those observations, and how useful they might be for constraining dark matter models. What I'm talking about today is a little bit different. So because of the speed gain from doing the sensitivity mapping with machine learning, we're able to prototype and test things much faster and try to find out a bit more about how this detection works. So that's what I'm talking about here. Essentially, we're going to set up 3 different detectors and produce sensitivity maps, test the sensitivity under different conditions, different model conditions. So I list the ingredients of the training data here on the right. Feel free to ask me about specifics of that at the end. Basically, there's a basic model where the lensing galaxy is an elliptical power law. So its angular symmetry is elliptical. And then there are 2 further models that include multipoles. So those are these 2 extra at the end. These are angular perturbations to the lensing galaxy's mass profile. So we allow these perturbations up to 1%, which is more of a realistic kind of model, and then also up to 3%, which is more just to see how the effect goes with stronger multipoles. And we're going to analyze these mock HST strong lens images using these 3 different models. So one doesn't know about angular complexity, one has some angular complexity, and then one has much more angular complexity. And I've shown out a sensitivity map basically from each of these models for the same observation. So this is a strong lens observation. The strongly lensed images are these white contours. And the color then is the smallest mass of dark matter substructure you could detect if it were there in that position at a 5 sigma detection significance. So the mass is indicated here on the color bar on the right. And the sensitivity map on the left, this is without any angular complexity beyond the elliptical power law that we normally use to do this kind of modeling. So elliptical symmetry only. You can see these bright spots here around the lens images. These are where you could detect the smallest substructures. Were they there? And now if we go to the model that includes some multipole perturbations, so now the lens is allowed to have angular complexity beyond just elliptical symmetry. And you can see that a lot of the sensitive area around the lensed images has now disappeared. So the region in which you could have detected a substructure now is much smaller. And that's because the signal in the lensed images produced by these substructures is very similar to the signal that you would get from adding a bit of extra angular complexity to the lens galaxy. They can kind of model each other away in this degenerate way. So the sensitivity really diminishes around here and further as you allow more extreme multipoles. But on the lensed images, on the arcs, you can see that the depth of the sensitivity, so how small of a substructure could we detect, does not really change. So that the brightest spot here on the arc is pretty similar to the brightest one here. So in terms of dark matter inference, what we want are the small substructures. That's what's useful for us to detect, because that's where dark matter models are the most different. And so in that sense, we expect to detect similar numbers of those when we include more angular complexity in the model. But we do lose an awful lot of detections around the lensed images, but they're these very large, fluffy objects, which don't provide much constraining power in terms of dark matter models anyway. So I think I'll finish there on my conclusion slide, and we'll take any questions.
Since we have 2 talks on the similar topic, we will have the second talk immediately following, and then please hold your questions until the end of this second talk.